بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله. This is review exercises about chapter 4, or if you want to call it chapter test. The first question: maximize the function f subject to the constraints determined by the shaded region shown in the figure. So we can see from the graph that there are two lines, and x is greater than or equal to 0 and y is greater than or equal to 0. And he gave us the intersection point between the two lines, 8 and 18. Now, this line, if I go below, so I reach 8 here, okay, and 18 is here, good. So, in the middle, because each unit of measure here is 4, so this is 20. All right. So you see that the axis, x-axis and y-axis are labeled. So we know that each unit of measure is 4. So this is 20 and this is 24. So the corner points are easy to find. This is one of them, and this is the second one, and this is the third one, and this is the fourth one. And you remember, to find the maximum of f, we just plot or substitute the corner points into the function f. So we make a table. I have the corner point 0 and 24. I have the corner point 8 and 18. 0, 0, of course. And I also have 20 and 0. And in the function f, I evaluate f at these values. So when x is 0, this would be 0 plus 5 times 24. And f would be 120 here. Well, here 3 times 8 plus 5 times 18, 114. 0, 0 will give you 0. And 3 times 20 is 60. And 5 times 0 is 0. What is the question? Maximize. So he is looking only for the maximum. So the maximum value of f is 120, and it occurs when x is 0 and y is 24. And this would be the answer of the question. Following are 3 simplex matrices in various stages of the simplex method solution of a maximization problem. Identify the matrix for which multiple solution exists. Identify the matrix for which no solution exists. For the remaining matrices, find the basic feasible solution. Use the variables x1, x2 and slack variables and the objective function until whether these values give the optimal solution. If they do not, identify the next pivot. So if this is this matrix a final matrix, or does it need more pivoting? Not final. So let us look to the first matrix A. We have 3 lines. So there are 3 slack variables, S3, S2, S1. And then there are 3 variables, X1, X2, and X3. Now, this matrix is not a final matrix because there are negative numbers in the indicators. So this is not a final matrix. So up to now, and it doesn't give an optimal solution. Uh, x1 is non-basic, so x1 is 0. x2 is basic variable, and this is the one. So x2 is 3 in this matrix. x3 is non-basic, so it is 0. And s1 is 6. s2 is not basic, so it is, we put it 0. s3 is basic and its value is 10. And the value of f is 50. And it is not a final matrix, not optimal. The solution is not optimal. So he said, is the solution optimal? No, it is not optimal. So to determine the next pivot, the most negative number in the indicators is this one. So this will uh, determine the pivot column. But now look to these numbers. 2 are negative and 1 is 0. So I cannot continue. So this system has no solution. The system has no solution. And if I just noticed this from the beginning, I would have immediately said the system has no solution. And all of these are not needed now because we cannot do another pivoting. Although if you write them, it's no problem. But we cannot do another pivoting, so the system has no solution. For this matrix, I still have a negative number here. So this is not a final matrix, and I can do pivoting in this case. I have three lines, three horizontal lines. So this is S3, S2, S1, and also I have X1, X2, and X3. Now X1 is, the value of X1 is 40. The value of X2 is 12, and it is a basic variable. X3 is non-basic and its value is 0. S1 is not basic and its value is 0. S2 is basic and its value is 20. S3 is not basic and its value will be 0. F is 170. And the solution is not optimal because there is a negative number in the indicators. So now this column will will be the pivot column. And now I divide 40 by 4 over 5. And the answer is 50. And I divide 12 by 1 over 5. And the answer is 60. So the smallest positive quotient here. So this row will be the pivot row. And 4 over 5 is the pivot entry. He said identify the next pivot. So 4 over 5 in row 3 and column 1, 2, 3, 4, 5, 6, okay, is the pivot entry or element. While here in this matrix, what do we have? Again, three rows. So S3, S2, S1, X1, X2, X3. Well, X1 here is 40, it's a basic variable. X2 is non-basic. And notice that it's not basic and the indicator is 0 of X2. So we put X2 0, but we immediately notice that this system or this linear programming problem has multiple solutions. So there will be multiple solutions whenever we have a non-basic variable with a 0 in, in the indicator line. So circle the pivot and specify all row operations with the pivot that are needed to find a second solution. So this is what he needs if it is if you have a multiple solution. So x3 is 60, s1 is non-basic 0, s2 is 15, s3 is non-basic 0, and f is 222. And this is a final solution, so this is the maximum value of f. But to get another solution, we can do a pivot operation using pivot column number 2. And if we divide 40 divided by 2, it's 20. 15 divided by 1 is 15. 60 divided by 3 is 20. So this number would be the pivot entry. So it is 1, and we use it to make 2 and 3 zeros. So 1 in row 2, column 2 is the pivot entry. And the row operations would be negative 3 R2 plus R3 and negative 2 R2 plus R1. And by this, X2 will be basic and S2 will be non-basic, and I will have another solution with the same value of f. Graph the solution region for each of the following. Well, this is a single inequality. To graph a single inequality, we make it an equation. We graph first the line. And to graph the line, I choose 2 points. I put x0, so negative 5y will be 30. Y would be 30 over negative 5. That's negative 6. And if I put y0, 3x would be 30, which means x is 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 and 0. And 0 and negative 6. This is 5, negative 5. So this is negative 6. So I just connect the 2 points. This is the graph of the line. And it's a solid line, not dashed, because there is an equality here. Now the graph of this inequality would be half a plane. It is either half a plane below the line or above the line. To find out, I choose 0, 0 and check it in the inequality. So 0 minus 0 is 0. Now 0 less than 30. Is that true? And the answer is yes. So the solution of the inequality would be this side. Okay, it would be this side, the side above the line. So this is the solution of the inequality, this part. Okay. X greater than 2, we need to graph x equals to 2, and that's a vertical line, this line, and it's dashed because there is no equality. And greater than means to the right. So all of this area is the solution of this inequality. Here I have 3 inequalities. So I need to graph each one of them. So the first one is 5. I'll graph the line 5y equals to x. And this means y equals 2 over 5x. And this line passes by the origin. If I put x0, I'll get y0. And now I'll choose x5. So y would be 10 over 5 or 2. And I can, okay, let me graph, or let me wait a little bit. I graph the other line, x plus y is 7. If x is 0, y is 7. If y is 0, x is 7. And the last line, 2y equals 5x. So y is 5 over 2x. Again, this line passes by the origin. If x is 0, y is 0. And if x is 2, y would be 5. So let me graph now the 3 lines and find the solution. So first line 0, 0, 5, 2. And the first line is solid, not dashed. It passes by 0, 0. So I cannot choose 0, 0. But I can choose, for example, this point, 0, 2, or 5, 0, whatever you like. Let me choose 5, 0. Okay. So let me put 5, 0 here in the first inequality. So y is 0, 5 times 0 is 0, greater than or equal to 2 times 5 is 10. This is not correct. So the solution is not below the line. The graph of this inequality, of the first inequality, is here, and this above the line. The second line, 7, 0, 0, 7, and it is a dashed line because there is no equality. Now, is it above or below? Is 0, 0 included or not? 0 plus 0 greater than 7, that's not correct. 0 greater than 7, that's not correct. So 0, 0 is not there, so the graph is to the right. So now I know that the graph is here in this region. But I need to see the third line. Well, the third line is a line passing by the origin 0, 0, 2, and 5. Okay, this point. 2, 5 is a point on this line because 2 plus 5 is 7. And also 5, 2 is a point on this line because 5 plus 2 is 7. So this is the line. It's not dashed because I have equation. So that's the third line. Let me choose 5, 0 also. So if I choose 5, 0 this time, y is 0. So 0 would be less than or equal to 5 times 5, which is 25. Well, that's correct. So 5, 0 is there. So this is the graph. So now where is the region that contains all of these conditions, satisfy all of these conditions? It is clear that it is this region between these two lines and up to here. So in this region, we are below this line and we are above this line and we are to the right of this line. So these points are the corner points, but they are not solutions in this case because this line is dashed. So this is the graph of uh, this system. Formulate the dual maximization problem associated with the following. So this is a minimizing problem, and to formulate the dual problem, I need to write the matrix for the dual problem first. To write the matrix for the dual problem, I write the coefficients of y1, 3, 4, and the coefficient of y1 in the objective function 2, and coefficients of y2, 5, 6, and in the objective function 3, and the coefficients of y3, 1, 3, and in the objective function it's 5. And then I write the right hand side. I have 100, 120, and the right hand side here is G. Okay. So this is the matrix associated with the minimization problem. Now, to formulate the dual maximization problem, I need to find the transpose of this matrix. And the transpose would be 3, 5, 100, 4, 6, 3, 120, 2, 3, 5, and G, or if you want to write it now F, because the maximization problem, I will call the function F. Now here I have x1 and x2. So there will be only two variables. So the problem would be maximize F equals 100, the objective row is taken from the last row, 100x1 plus 120x2, subject to, and there will be three constraints, 3x1 plus 4x2, and the important thing now, this is a maximization problem, so in the standard form, we write it less than or equal. And also the minimization problem in the standard form is greater than or equal to a positive number. So this was, or this is a minimization problem in the standard form, and that's why we can't find its dual. The second constraint, 5x1 plus 6x2 is less than or equal to 3. And the last constraint is this one. And of course, you can say that x1 is greater than or equal to 0, and x2 is also greater than or equal to 0. So this is formulate the maximization problem. This is the maximization problem associated with the minimization problem. Find the maximum and minimum values of this function if they exist, subject to the constraints. Well, there is no maximum because it goes to infinity. The region is open, not bounded. But we can find the minimum. But to find the minimum, we need to determine the corner points. And there are 4 corner points. And the x-axis is not labeled and the y-axis is not labeled. So I'm not sure what is this. Is it 1? Is it 2? What is the unit of measure? So to find this point, okay, I'll find the x-intercept of this line. This is the line x plus 3y equals 15. If I put y 0, x would be 15. So this point is 15. So I know now that the unit of measure is 3 because this is 3, 6, 9, 12, and this would be 15. But the unit of measure is not important here. The important thing is to determine the corner points. And I know now that one of the corner points is 15 and 0. And I need to determine this one. And it is the y-intercept of a straight line. What is the equation of this straight line? Yeah, it is this one, 4x plus y equals to 12. To find the y-intercept, I put x0, so y is 12. So I know now that this is 12. 3, 6, yeah, also you can notice that the unit of measure is 3. So anyway, 0 and 12 is another corner point. And now to find this corner point, it is the intersection between this line, which is 4x plus y equals 12, and this line, which is x plus y equals to 9. And if I just subtract, 4x minus x is 3x, y minus y is 0, 12 minus 9 is 3, so x is 1. And if I put it in the second equation, y is 8. So actually this point is 1 and 8, has coordinates 1 and 8. And it is okay. It seems correct. Now the last corner point would be this one. So this is 1 and 8. Okay. And this one is the intersection between this line, which has x plus y, equation x plus y equals to 9, and this line, which has x, equation x plus 3y equals to 15. And also we can subtract easily x minus x 0, 3y minus y is 2y, and 15 minus 9 is 6. So y is 3, and if you put it in the second equation, x would be 6. So this point has coordinates 6 and 3, and also it seems correct. So 6 and 3 is the last corner point. And now we are ready to put them in the function f and to find the minimum value because there is no maximum, because the area is not bounded. Well, if x is 15, 5 times 15 is 75, and y is 0, so f here is 75. If y is 12 and x is 0, f is 24. If x is 1, so I have 5 times 1 plus 2 times 8. So I have 21, the value of f. If x is 6, 5 times 6 is 30, plus 2 times 3, so 36. So it's clear that the minimum value of f is 21, and it occurs when x is 1 and y is 8. I'll stop here and continue in another video.